It's funny. When we usually think about a computer simulation, like an open world video game or something, we always expect these rigid boundaries.
Right, yeah, like hitting the edge of the map.
Exactly. You walk to the edge, you hit an invisible wall, and the game essentially just points and says, that's it. End of the world, turn back.
Right, which is comforting in a way.
It is. We're comfortable with that because it gives the sandbox a definable shape. You know where things end.
Well, and mathematically speaking, it provides a container. In physics, having that rigid boundary makes calculating things like the total energy or the information inside that container just significantly easier.
Because you always know exactly where the edge of your reality is.
Precisely. You have a fixed reference point.
But then, you tip out of the video game and you step into the world of actual cosmology and theoretical physics, and suddenly that invisible wall is just gone.
Yeah, totally vanish.
Making videos is no easy task, and thinking independently is even harder. If you're able to, please show your support by checking out the products from the Zero Dimension shop link at the bottom left of the video.
And I imagine that really messes with the math.
Oh, it absolutely does. It turns the fundamental rules of quantum mechanics and gravity into this moving target. I mean, if you can't anchor your calculations to a wall, you have to entirely rethink how information is stored in the universe.
Which is exactly what we're getting into today. Welcome to today's deep dive, where we are taking you right to the absolute bleeding edge of theoretical physics and quantum computing.
It's a heavy stack of research today.
It really is. We are looking at a stack of incredibly dense, just paradigm-shifting research, all centered on a single massive question, which is, how is reality constructed at the quantum level, and can we build it ourselves?
Which sounds like sci-fi, but it's very real.
Totally. So we're exploring Leonard Susskind's paper on de Sitter space holography, which is basically the physics of our expanding universe. Then we're looking at William Harvey and Kristen Jensen's work on manipulating the fabric of spacetime to create actual 3D traversable wormholes.
Yeah, that one is mind-bending.
And finally, a breakthrough paper by Thomas Schuster and his colleagues on performing many-body quantum teleportation in a literal laboratory.
Right here on Earth?
Yeah. So the mission for this deep dive is to really understand how the mind-bending mathematics of quantum gravity are, stepping out of the chalkboard realm and into actual near-term quantum computer experiments. We're going from the shape of the cosmos to a microchip.
It's a huge leap, but the math connects it all.
Okay, let's unpack this. Because before we can even talk about building a wormhole in a lab, we have to understand the shape of the universe we're actually trying to simulate.
Right. And to appreciate what Susskind is doing with our universe, we kind of have to look at the shortcut physicists have been using for decades.
The snow globe thing, right?
Basically, yeah. It's called anti-de Sitter space, or ADS. In holographic physics, ADS is incredibly popular because it acts exactly like that video game with the invisible wall.
It has a hard edge.
Exactly. It has this cold, rigid, asymptotic boundary. And the holographic principle suggests that the 3D reality we experience is actually projected from 2D information living on a boundary.
Okay, so in ADS space, that information lives comfortably on that outer immovable glass wall.
Yeah, it's very neat and tidy.
So ADS is basically a snow globe. You have this clear glass boundary enclosing everything. And the fundamental bits of information, the degrees of freedom, are basically painted on the inside of the glass.
Right, projecting the snowy scene in the middle.
But Susskind points out the massive elephant in the room here, which is that our actual universe isn't a snow globe.
Not at all. We do not live in anti-de Sitter space.
Right, we live in de Sitter space, or DS. Our space is expanding. There is no cold, rigid glass boundary. Like I said earlier, we are standing in the fog.
And the only boundary we have is a cosmic horizon, which is just the absolute limit of where light can ever reach us before the universe expands too fast.
And that creates a massive problem for the math, right?
A huge mathematical crisis for holography, yeah. Because of this, Susskind had to completely rewrite the fundamental tool we use to measure quantum entanglement.
This is the Ryutakiani formula, right?
Yes, the RT formula.
Okay, hold on. My brain is melting a bit with the jargon here. Let's make sure I'm picturing this right and that you at home are picturing this right. What is the RT formula actually doing, like physically?
Okay, think of dipping a uniquely shaped wire frame into soap and pulling it out.
Oh, like making bubbles.
Exactly. A soap film naturally forms across the wire, and it always finds the configuration with the absolute minimum surface area.
Okay, that makes sense.
The RT formula does exactly this, but mathematically. It calculates the entanglement entropy between two regions of space by finding a minimal surface, like that soap film that separates them.
Right.
But here's the catch. In the ADS snow globe, the wireframe, the anchoring points for that soap film, is pinned to that outer glass wall.
Ah. And in our expanding de Sitter universe, there is no glass wall to anchor the wireframe to. So where does Susskind actually pin the soap film?
Well, he proved you have to move the anchoring points inward. You pin them to what he calls the stretched horizon itself.
A stretched horizon.
Yeah, it's this conceptual layer hovering just a microscopic fraction above the actual unobservable cosmic horizon.
Okay, and this leads to my absolute favorite visual in these sources, which is the bit thread picture.
Oh, yeah, the bit threads are a great way to visualize it.
The paper says that if you want to visualize this entanglement entropy, don't just think about soap films. Imagine a network of microscopic tubes, like each the size of a plank length.
Just unimaginably small.
Right. And you were trying to pump water or push these microscopic threads from one region to another through a bottleneck.
Right, and the absolute maximum number of these non-overlapping bit threads you can squeeze through that bottleneck gives you the entanglement entropy.
So what changes with Suskind's new anchors?
What's beautiful about his modification is that because our anchors are now on the stretched horizon, the bottleneck literally is the horizon.
Oh.
Yeah, you are squeezing those bit threads right along the edge of the observable universe. And this structural shift radically alters how information behaves over time in our universe.
Specifically regarding a process called quantum scrambling, right? I want to make sure we nail this concept because scrambling comes up a lot today.
It's fundamental to all of this.
So scrambling is essentially how fast information spreads out and becomes totally chaotic across a quantum system. Like dropping a single bead of black ink into a glass of water and measuring how long it takes for the entire glass to turn gray.
That's a perfect analogy. And in the ADS snow globe model, scrambling takes a very specific amount of time. The math says it's proportional to the radius of the space multiplied by the logarithm of the system's entropy.
So R log S.
Exactly, R log S.
Right.
And that math actually represents a physical journey.
Like things actually moving.
Yeah. The log S factor isn't just a random variable. It represents the time it takes for a piece of information, like a single particle, to literally fall from that outer glass boundary all the way down to a black hole in the center where it can finally be scrambled.
Wait, but in de Sitter space, we don't have that fall. There's no glass wall to fall from.
Exactly. Susskind notes that the simple degrees of freedom, the fundamental bits, are already at the stretched horizon.
So there's no travel time. The ink is already in the water.
Precisely. So that log S factor completely disappears from the equation. Scrambling in our universe happens in a hyperfast time of just order R.
Hyperfast scrambling. That is wild.
And it isn't just a mathematical quirk, you know. It is the holographic dual to the exponential growth of space behind our cosmic horizon.
Meaning what exactly?
Meaning the geometry of the universe is stretching outward so aggressively that the underlying quantum complexity, the shuffling of information at the horizon, has to operate at this hyperfast speed just to generate enough space-time to keep up.
Wait. So if the fundamental degrees of freedom are scrambling right at the horizon, does that mean our reality is essentially being projected inward from the very edge of what we can observe?
Yes.
Like the fog itself is generating us?
That is the core implication of the static patch holography model Susskind is exploring here. The reality you experience in the center is encoded at the extreme limits of your observable bubble.
That is deeply unsettling, but also amazing.
It is. And to ground this mathematically, Susskind employs a framework called the SYK model.
Right, the SY2 model.
You can picture the SYK model as a chaotic web of quantum dots, where every single dot is randomly interacting with every other dot simultaneously.
Look, to make this model match our hyperfast expanding universe, he introduces this fascinating thermodynamic state. He calls it temperature.
Temperature, yes, with an M.
Right, with an M. So what actually happens to a system when you crank it up to temperature?
Well, in classical physics, if you raise a system's temperature to infinity, everything just burns out into pure structureless white noise immediately.
Right.
Right?
Right, it just boils away.
But temperature is a specific mathematical limit where the traditional temperature goes to absolute infinity, ensuring maximum chaos, but the energy per particle and the physical timescales of the system remain strictly finite.
Oh, I see. So it is a balancing act.
Exactly. It allows the SYK web to scramble information as fast as physically possible without instantly dissolving into meaningless noise.
It's incredible. We are basically living inside a hyperfast quantum blender that projects reality inward.
That's one way to put it, yeah.
So if spacetime and geometry are just, manifestations of this entanglement happening out at these horizons, it begs a massive question. What happens if we artificially manipulate that entanglement?
Like, could we hack the geometry?
Exactly. Could we hack it? Which naturally transitions us from the massive cosmology of de Sitter space to the second batch of research. William Harvey and Kristen Jensen looked at these holographic boundaries to see if they could manually stitch them together to create a traversable wormhole.
Wormholes, yeah. They have plagued theoretical physics since Einstein.
Because mathematically, a wormhole is a shortcut through spacetime connecting two distant points.
Right. But the problem is they're famously not traversable. They are strictly forbidden by a rule called the averaged null energy condition, or ANE.
ANE?
Yeah, you can think of ANE as gravity's immune response. Gravity absolutely abhors traversable wormholes.
So if one tries to form, gravity just kills it.
Instantly. If the geometry for one begins to form, gravity forcefully pinches it shut so violently and so quickly that not even light can make it through to the other side.
But Harvey and Jensen found a loophole.
They did. They employ a technique called the Gauss-Jafferis wall double trace deformation.
Which sounds incredibly intimidating.
The math here gets wild, I won't lie. But the concept is basically quantum stitching.
Right, quantum stitching. Imagine you have two entirely separate holographic boundaries.
Right.
Let's call them the left universe and the right universe. You take a microscopic mathematical thread, which is specifically a negative energy interaction, and you directly couple the matter fields of the two boundaries. You are literally sewing the two universes together.
And by applying that specific negative energy stitch, you introduce a highly controlled violation of gravity's immune response, the ANEC rule.
You trick it.
Basically, you are artificially feeding the throat of the wormhole the exact exotic negative energy it needs to resist gravity and stay propped open eternally.
That is just brilliant. And what Harvey and Jensen did was prove this works by reducing the immense complexities of 3D gravity down to a 1D boundary theory.
Right.
The sources mentioned they use a U1 cross U1 gauge symmetry that expands out to an SO2 symmetry.
Which is a mouthful.
Yeah, for anyone not holding a PhD in group theory, how do we visualize what they actually tracked there?
Okay, picture the boundary of each universe as the surface of a pond. When you introduce energy, you create ripples. In gravity, these microscopic ripples on the boundary are called boundary gravitons. So instead of trying to calculate the entire 3D volume of the wormhole, which is too complex, they just tracked the geometric symmetries, the exact mathematical patterns of the ripples on the left pond and the right pond.
And the SO2 symmetry.
When you apply that quantum stitch, the SO2 symmetry shows how the ripples perfectly synchronize across both ponds, proving that a physical bridge has formed between them.
Oh, wow. But the stitch has to be perfect, right? Because the research highlights a strict stability condition using the Greek letter delta.
Yes, delta is crucial.
So if delta represents the weight or the dimension of that quantum stitch, what happens if delta is greater than 1? Like, if the thread is too heavy, does it just tear the fabric apart?
That is precisely what happens. If the operator supporting the wormhole has a delta greater than 1, the math shows that the lighter mass mode of those boundary gravitons becomes tachyonic.
And tachyonic is bad.
In physics, a tachyon mode indicates catastrophic instability. The ripples spiral out of control. The wormhole effectively rips itself apart before a signal can even cross. So the stitch must be incredibly delicate.
And if you get the stitch exactly right, something wild happens, according to the paper. There is a phase transition.
This is where the underlying math dictates physical reality. The strength of your coupling, like how tight you pull that quantum stitch, determines what actually exists.
Really?
Yeah. If your stitch is too weak, the math just describes two completely disconnected black holes. But as you increase the coupling, you hit a critical threshold.
The phase transition.
Exactly. A mathematical phase transition occurs, and suddenly the connected wormhole saddle point overpowers the disconnected state. The two black holes literally snap together into a single dominant wormhole tube.
They just snap together. That mathematical loophole is the perfect setup for the third paper in our stack.
Oh, absolutely.
Because if we understand the exact mathematical parameters required to stitch two boundaries together and create a wormhole, we don't have to search the cosmos with a telescope to find one.
We can build one.
We can literally build this exact coupling inside a quantum computer in a lab. This is the paper by Thomas Schuster and his colleagues on the Traversable Wormhole, or TW protocol.
Right, and the TW protocol takes everything we just discussed and turns it into actual experimental engineering.
So how does it work?
Well, you start by taking your quantum processor and splitting it into two halves. You initialize them into what is called a thermofield double, or TFD state.
Which means the left side of the chip and the right side of the chip are perfectly maximally entangled. They are acting like two identical synced-up universes.
Precisely. And once they are synced, you introduce your information, like a single qubit, into the left side.
Okay.
You allow the left side to evolve and scramble that information entirely, spreading it out among all the other qubits.
So it's lost in the chaos.
Seemingly, yes. Then you apply the quantum stitch. You measure the state of the left side, and you use a classical wire to send a pulse to the right side, applying that negative energy coupling.
And when you do that, the information that was completely scrambled on the left side magically coalesces, unscrambles, and pops out perfectly intact on the right side.
It teleported.
But Schuster's paper drops a massive bombshell right here. They reveal that when you run this protocol, there are actually two entirely different mechanisms that can cause the teleportation.
Right. From the outside, they look identical. You put a qubit in, and a qubit pops out.
But underneath the hood, the physics are wildly different.
Very different.
Yeah.
The first mechanism is gravitational teleportation. This occurs in systems operating at very low temperatures that are mathematically dual to semi-classical gravity.
Okay, so this is the real deal.
Yeah. When you run the TW protocol here, you are genuinely simulating the geometry of a traversable wormhole. The qubit is literally passing through a microscopic geometric throat.
And how do they know? Like, what's the signature of that?
The signature is incredibly distinct. You get a single, massive, isolated spike in teleportation fidelity exactly around the scrambling time. And because it's a wide geometric throat, you can actually send multiple qubits through at once.
Okay, but then Schuster's team details this brand new second mechanism. They call it peaked size teleportation. And this is fascinating because it achieves teleportation without any gravity or wormhole geometry whatsoever.
Not at all.
How does that even work?
It relies purely on the statistical chaos of quantum mechanics. Let's go back to your analogy of dropping ink into water.
A scrambling analogy. Yeah.
Right. When you drop a qubit into a chaotic quantum system, the mathematical operator representing that qubit begins to grow and spread out, just like the ink.
Okay, following so far.
Now, if the statistical distribution of that spreading is tightly peaked, meaning almost all the microscopic ink particles are spreading outward at the exact same uniform mathematical rate, an amazing thing happens when you apply the stitch.
Right, because applying the stitch, that coupling between the two sides, it acts as an overall phase shift. But how does a phase shift unscramble the ink?
Because the ink is spreading at a perfectly uniform rate. Applying a uniform phase shift perfectly inverts the momentum of the spread.
Oh, wow.
It essentially hits reverse on the video. The chaotic system perfectly rewinds, the ink particles gather back together, and a pristine drop of ink pops out on the right side of your quantum computer.
That is wild.
It's a teleportation driven entirely by statistical operator spreading, not gravity.
And this solves a massive mystery in the field, right? Physicists had noticed that the SYK model, the web of interacting particles Susskind used, could still successfully teleport information even when it was heated up to high temperatures.
Right, and high temperature SYK isn't dual to gravity.
So it couldn't be a wormhole.
Exactly. Schuster proves that at high temperatures, the SYK model automatically defaults to this peak size mechanism.
But it raises a huge practical question for me. If I am an engineer, right, and I run this TW protocol in a lab tomorrow, how do I know if I actually created a microscopic gravitational wormhole, or if I just executed standard peak size quantum rewinding? They both result in teleportation.
It is the most critical question for the experiment, and Schuster lays out the diagnostic blueprints to tell them apart. You have to meticulously track the fidelity of the teleportation over time.
Fidelity meaning how perfectly the information was transferred.
Yes. If your system is just doing generic peaked size teleportation, the fidelity isn't a single clean spike. As the operators spread, the signal oscillates rapidly. It rings like a bell, bouncing between 0 and a baseline value known as the 2-point function of the system.
So it's messy. It's a noisy, oscillating wave.
Very noisy. But in true gravitational teleportation, all of those noisy oscillations vanish entirely.
The geometry dampens them out.
Yes, the geometry dampens them out. You just get that one massive, singular, smooth spike in fidelity. And what is truly profound in Schuster's analysis is what happens when you blend the two.
What do you mean?
If you take the gravitational model and you start adding stringy corrections, meaning you make the underlying physics less like pure, smooth Einstein gravity and more fuzzy, like string theory, the math seamlessly interpolates.
So the spike changes.
Yeah, the singular spike of gravity slowly begins to melt into the oscillating waves of peaked size spread.
That is just, it's beautiful math. Okay, so what does this all mean for you, the listener? Why are we spending an entire deep dive talking about de Sitter horizons, stringy corrections, and 3D wormholes when this show usually focuses on near-term technology?
Because it is near-term technology.
Exactly. Sure. Because the Traversable Wormhole protocol isn't a chalkboard thought experiment anymore. Schuster's paper provides the literal blueprints for running this on quantum simulators that exist right now.
Yes, specifically they point to trapped ion quantum computers and Rydberg atom arrays.
Let's talk about the Rydberg atom arrays.
Sure. A Rydberg atom array is a device where scientists use highly focused lasers to trap individual neutral atoms, often rubidium, in a vacuum, arranging them in programmable grids.
Right.
By pulsing these atoms with specific microwave frequencies, you can make them interact and entangle, perfectly simulating models like SYK.
So we aren't just using quantum computers to, factor large numbers or calculate chemical bonds anymore. We are using them as literal universe simulators.
That's exactly what they are becoming.
We can boot up an array of rubidium atoms, perfectly entangle them into a thermofield double, manually apply a Gauss-Jeffreys wall negative energy stitch, and literally watch a qubit traverse a wormhole on a microchip.
And if we connect this to the bigger picture, it is breathtaking. The scientific community is using near-term quantum hardware to test the most fundamental assumption of modern physics.
Which is?
The idea that space-time itself, the fabric we exist in, is merely a byproduct of quantum entanglement.
Just a byproduct.
Yeah. By successfully running the TW protocol on a Rydberg array and
making videos is no easy task, and thinking independently is even harder. If you're able to, please show your support by checking out the products from the Zero Dimension shop link at the bottom left of the video.
Who showed us that our expanding de Sitter universe scrambles information hyperfast out at the cosmic horizon, essentially projecting our reality inward from the fog.
Right.
Then Harvey and Jensen showed us the underlying mathematics of how to hack that projection, how to sew those holographic horizons together with negative energy to stabilize a 3D wormhole.
The quantum stitch.
The quantum stitch. And finally, Schuster and his team handed us the actual instruction manual to build those wormholes inside a trapped ion computer today, giving us the tools to distinguish a real geometric wormhole from a statistical trick of peaked size operator spreading.
It represents a profound, unprecedented convergence of theoretical cosmology, quantum mechanics, and experimental engineering. We are finally building the sandbox.
And it leaves me with one final, deeply provocative thought for you to chew on today.
Oh, lay it on us.
Think back to that video game fog we started with. Let's say a team in a lab flawlessly executes this protocol on a Rydberg atom array, but they don't get the gravity spike. They perfectly simulate the exact mathematical conditions of peak size operator spreading.
Okay, so the ink perfectly rewinds.
Exactly, the ink rewinds. A physical qubit successfully teleports from one end of the microchip to the other, moving from point A to point B without crossing the space in between. If the mathematical parameters are perfectly identical and the physical result of teleportation is identical.
I see where you're going with this.
Is there a meaningful difference between a simulated space-time inside a quantum computer and the physical space we currently live our lives in?
Oh, wow.
Or is reality itself just complex operators spreading across a vast universal quantum circuit, projecting everything we know out of the fog?
Now that is a question worth exploring.
Thanks for joining us on this deep dive.